wait, what's this thing? You say using like I didn't apply to graduate for like semester 1. I got it semester that week. So you're supposed to apply like before your last semester, so what did you apply? So before the semester? Or whatever. Oh, okay, so Stephen can easily pass all of yeah. So Stephen can pass all his classes, but he has to wait. He has to do nothing for another semester. He graduated in the fall. Summer.
It's okay, David. I think David's made a lot.
Well, yeah.
Alright guys, let's get started.
No, let's talk about it.
Let's get started. So first off, the TAs are still graded. However, they have expressed a concern to me that there's a lot of sloppy handwriting. And I looked at some of the sloppy handwriting, and I'm not one to talk. But the issue that it's causing is you look at everything, and it looks like they got the right idea and they're right, but then you can't read key words. And if you can't read key words, you can't give the benefit of the doubt. So just to warn some people out there, there's been a couple examples where we want to give you points, but because we can't read the explanation, we don't give full credit because we don't know what you're saying. So just to warn some people when they pick up their exams next week. Again, I'm not one to talk, but oh well. So just real quickly reviewing the Wittig reaction. We talked a lot, almost entirely about the Wittig reaction. Remember, a Wittig reaction is a reaction between a phosphorus ylide and an aldehyde. Alright, and the phosphorus ylide, as drawn here, is going to have a partial minus charge at the carbon and a partial positive charge at the phosphorus, and we've talked about this ad nauseum. And then what happens is the ylide can attack the aldehyde two different ways. So first off, it's going to always attack the aldehyde so that the triphenylphosphine, which is the biggest part of the ylide, sterically speaking, is going to be pointed towards the hydrogen. So the big part's going to always be pointed towards the hydrogen to minimize the interaction with it. But then they can either attack like this, where the hydrogen's pointing towards the R group, or the R is pointing towards the oxygen, or it can attack like this, where the R group is pointed towards the R group and the H group is pointed towards the oxygen. So this is the lower energy attack because in this case we only have a steric interaction between a hydrogen and an R group. This is the higher energy attack because in this case we have an interaction between two R groups. So this is higher energy than this. So it will attack with the carbon attacking the carbonyl, the electron density kicking up to the oxygen, and the oxygen attacking the positive charged phosphorus to give us our four-membered ring. And so from this transition state, this gives us the four-membered ring in a puckered conformation. But to really understand it, we have to draw it not in the puckered conformation, we have to draw it in the flat conformation. And the best way to do this, and I told you this in lecture and I'll show you it again, in this case, this thing, if you relax the bonds and you move this forward, so pretty much you're bringing this up and rotating this bond forward, we're going to get a side-on view that's going to look like with the phosphorus on top going to here. So this hydrogen, as we rotate this bond and flatten this out, this hydrogen will be pointing here. This R group will be pointing here. Orange. All right, and then naturally, we're not moving this at all. So in this case, this hydrogen is still going to be pointing this way, and this R is going to still be pointing this way. And so what this means is, for this attack, giving us this thing when we flatten it out. We actually have a four-membered ring where the hydrogens are on the same side and the R groups are on the same side. So what this means is this is going to go and then collapse to give us triphenylphosphine oxide and our trans-olefin, sorry, our cis-olefin. Because this step where this breaks down to triphenylphosphine oxide and the double bond is concerted, so atoms don't move, just like in the Devil's alder. So when it breaks down, if the R groups are on the same side in the four-membered ring, they're going to be the same side of the olefin. So that's why we get the trans. In this case, if we do the same analysis, I'll do it fairly quickly. Again, if we flatten this out, the R group will be pointing this way, and then the hydrogen will be pointing this way. And of course, nothing changes with the green part for the aldehyde, what was the aldehyde. And so now when you flatten this out, you now see that the R group and the R groups are now on opposite sides. All right, and so when you do the key step, the square dancing, if you will, for this, you get triphenylphosphine oxide plus the trans. And I've not drawn triphenylphosphine oxide, but just know it's there. And so we get the trans. So that's pretty much all I discussed on Wednesday in one slide. The only thing I changed, and so what I also discussed, before I forget, was because this is the lower energy attack, but gives you the less stable four-membered ring because the two R groups are on the same side and are giving you a steric interaction. This will be a lower energy attack that gives you a higher energy product, which means it will be the kinetic product. All right? This is a higher energy attack because of sterics that gives you a lower energy product. So this will be the thermodynamic. So the last thing I'm going to say about this is with the Wittig, to get kinetic thermodynamic, you can't switch just by adding heat. The Wittig's not like that, mainly because the intermediates aren't stable with heat, so you won't get a good reaction. The way you switch from kinetics to thermodynamics in the Wittig is by the substitution of your R group on the phosphorus ylide. If the substitution on of the R group in the phosphorus ylide is electron withdrawn, now when you form your higher energy four-membered ring, it can go back. And the reason it can go back is because remember there's a lot of partial minus charge in the ylide. If this is an electron withdrawn group, this is going to be more stabilized than if it's an electron donating group because of the partial minus charge adjacent to it. So when you have an electron withdrawn group, it will take less energy to go from the four-membered ring back to the starting materials. So it will be easier for the reaction to be reversible at this phase if you have an electron withdrawn group. So if you have an electron donating group, it will do this first and it won't be able to go back. So you get your trap, your cis product. If you have an electron withdrawn group, it will do this first as well, but it will actually be able to go back and eventually funnel towards the more stable intermediate, giving us the more stable product. So that's why electron withdrawn groups give us the more stable product. There's one, for why electron withdrawn groups give us trans, there's one more argument. And I wasn't going to tell you guys, but I told people in my office hours and they seem to like it. So I'm just going to say this real quickly for the other argument for why electron withdrawn groups give us the trans. So if this R group is an electron withdrawn group, how do you think that will affect the acidity of this hydrogen adjacent to electron withdrawn group?
More acidic.
It'll be more acidic. And if it's like a nitro group or a nitrile or even ester, it's going to have a pKa of about 20 or lower. So, if this is not the neutron group, this is the acidic proton. So now you can imagine perhaps some base in your solution can deprotonate this, giving us an anion. And remember, anions are not conformationally stable. They can invert. So the other argument is when this is acidic proton, a base will come and take this hydrogen, giving us an anion, which will then flip to the more stable conformation and then become reprotonated. Does that make sense? So with this, if this is an electron group, the base can take this and give us an anion. Where's blue? PR3. It will take the proton and give us an anion. But anions can flip, right? Anions have a fair bit of sp2 character. So this anion, and I've said this a million times in the class, anions can flip, they can become flat, and then they can invert. Anions can invert, anions can invert, anions can invert. No, I really said it many times in the class. So because anions can invert, this can now flip from the cis to the trans 4-membered ring, and then the trans 4-membered ring can be protonated, and that's going to give us a thermodynamically more stable intermediate, and then that will go collapse and give us our trans. So the other argument is when we have an electron group here, the proton's acidic, and so we can deprotonate it and racemize or scramble the stereochemistry to eventually give us the more stable intermediate. Okay, that was a lot. And I like the solid faces. All right. So now we're in chapter 17. Chapter 17 is more fun with adding things into pi systems. So chapter 16 was adding things into aldehydes and ketones. Chapter 17 is adding things into carboxylic acids, amides, and related compounds. So this chapter is going to deal with carboxylic acids, esters, amides, acid chlorides, and hydrides. Acid and hydrides, acid chlorides. Let me do a different color. Come on, liven up. You guys are in awesome Chem 432 class, right?
Yeah.
Amides. Or let's put it this way: SDSU is going to destroy St. John's today.
Hell yeah!
Esters. I hope that Dwayne Polly scores like 20 points, since he actually started at St. John's back in the day. Although it took 2 hours for my bracket to be destroyed. And the rest of America's really. Alright, so we're dealing with these carboxylic acids and carboxylic acid derivatives that have a carbonyl attached to one carbon-based substituent and one substituent that's not carbon or hydrogen. So OHs, OMEs, amides, chlorides, and anhydrides. So basically, the first thing the book really goes over, and I'm only going to gloss over it, is the pKa effects of carboxylic acids. So the big thing that they got well again is the effect of electron withdrawing groups adjacent to carboxylic acids. So in general, what do you think the effect on the pKa of a carbon? First off, what's the typical pKa of a carboxylic acid?
4.5.
4.5. That's a good number. I think it's 4.75, but 4.5 is solid. So a typical carboxylic acid has a pKa of about 4.5. Is an electron withdrawing group on the carbon adjacent to an acid going to make it higher or lower? Lower. And is it going to be through a resonance?